Okay. Is this working? It's not working. Hello? This time it seems to be working. Okay, good morning. Yeah, our system need to reboot because otherwise it will not project it, so we can wait for 1 or 2 minutes. Okay. Before that, I should mention about the assignment. Okay. The assignment, some students, which is nice, is already look at the programming assignment. Actually, some people have tried. Okay. So there are several things I should mention. Okay. The first thing is somebody asked about the program languages. For program languages, we say it is very flexible. We ask you to finally upload the source code, but we do not give you a very specific requirement. You can write in Java, in C++, in Python, even in R, any language you think is reasonable. I think TA already in Piazza answered that question. Okay. So basically, you should try to use something reasonably popular, okay, which is benefiting you as well, because you can, if you get any problem, you can ask for help from either TA or from your classmate. Okay. Then one student actually tried, which is good. I think the student sent me an email, said he tried the PageRank on several testing things he or she tried, and found the answer on the top 10 is more or less the same. Actually, this is what we want you to try, okay? Because we proposed a new measure which is more sensitive, but we need a comparison. We actually want you to compare both very popular measures, personalized PageRank, and SIMRank, just because the SIMRank cannot run on very large database, like it runs forever, can never stop. So we finally turn everything just to personalized PageRank. But we actually want you to test it to see how you will run it on different data sets to see as a proof. As a proof, the newly proposed measure is better. Okay. So you program on the real data sets, you really see the differences. Okay. So I would strongly suggest you to start early. The reason is we actually were ask you to hand in this one after. It's not before the midterm, it's after midterm, because I checked the date. Our midterm is March 1st, and our due date is March 7th. Essentially, even after midterm, you have 7 days to work on. But I strongly suggest you to do it earlier, because there are many questions. If you did it, you get better understanding, so you will be more confident to handle midterm questions. If you did not do it, okay, the midterm question may be something quite similar. You will get suffered. Okay, so that's why I suggest you start early. Okay, feel free. You can discuss with me, with anybody on this. We welcome discussions, even you do it independently. Okay. Another thing is about the survey and research project proposal. Okay. We said it's 1 page. Of course, if you say I can never write 1 page, that's short. I need 1 sheet. I need 2 pages. That's fine. Okay. We just want you to write very short. It should have title. Should have the abstract. Abstract is you can outline the major things you want to do, why you want to do it, and you need a set of references, like 5 or 10. I think usually 5 is good enough, because we clearly see whether you have read something, you know something, you want to do something new. Okay, and this will help us, because we do not give you a concrete score on this grade, but we'll give you suggestions. Another thing is you should really use my office hour and TA office hours to discuss with us, okay? Because sometimes the discussion, you have a proposal, you discuss with me. Maybe I said, oh, somebody has done it. You better do it, a little further. I can give you suggestions. To that extent, you will save your time, because sometimes you work on this for weeks, finally found somebody has done it. Okay, then you have to do something new. Okay. Research is always like this. You have to do a very good survey before you really delve into the new frontiers. So that's why I strongly suggest you line up the survey with your research. That means you want to do this research, you first read a lot of papers, you write a survey. Okay. Write a good survey actually will help your research quite a lot. Okay, so that's about our requirement. Hopefully you can hand in high quality. Okay. Even we do not give you the concrete grading, I should say sometimes it's more than grading, because you get help, it will save your time. Okay. Now, starting this lecture, I'm going to discuss more on the things we are really interested in. We have been doing this for years. This is about mining heterogeneous information networks. Yeah, this one actually, if you do not know, this one is in the summer in Oslo. This is a big stadium for the high ski jumping. Actually, the angle I took the picture was I stood on the very top. This is almost the starting point of those skiers. Okay, the ski down, of course, in the winter is all covered with snow. The ski down. And then right in the center, they started doing all the, turning around, several rounds. Then they finally land on right in the center. The nice thing is, when a few years ago, I think 2 years ago, I showed this picture in class. Right after class, one student showed me the picture exactly the same picture right in the winter. Actually, he was an Olympic player. Okay, he actually won the 2010 Winter Olympics on the speed skating. He actually was an excellent student. He got, in this class, he got a paper. Not only he got A+, actually I was very surprised because the year he was preparing the Winter Olympics 2014, he told me he may miss several classes, and sometimes they miss quite a number of classes because he has to do the training. But he said he would struggle, try to finish the course on time. To my own surprise, finally I grade him, he got A+. Okay, it's one of the best in the class. And then in this class, he got a paper published in 2015, EDBT, got the Best Paper Award. Okay, Best of EDBT. They selected and invited journal. And now he's doing PhD in Stanford. So he did it win Winter Olympics. That's why he said that's his training place. Okay, that's in Oslo. That's why he took the picture. I love this picture, but I love his picture in the winter. It's much better than I took in the summer. Okay. That's Jonathan Cook. Okay, it's one of the best students I ever have as an undergrad student here, and directly go for a PhD in Stanford. So let's start on the information networks. Okay. The first thing, of course, we already study a lot of networks. You know the whole web is a big network. Facebook is a big network. And we actually got into biological networks, co-author networks. There are so many networks. It's so big and so information rich. So people are actually getting into this network science quite a lot. But the interesting thing is, a lot of people studying networks, they think every node is of the same type, like a web page. Okay. Then the links means similar things, like Facebook. You link to them, that's my friends. Okay. So the links actually means the same friendship relationship. Okay. But actually, if you really go back to think about many, many networks, they may not look like that. Okay. I'll just give you a simple example. If you got, say, a research paper, I just grab one research paper from PubMed. The PubMed is medical publications. How many papers in this PubMed? I do not have a concrete count, but people say it's more than 30 million papers in this repository. Okay. And every year, the incremental of the paper is about 1 million. Okay, so that's a research paper. Nobody wants to read a 1 million paper a year, right? So what you do is you have to develop some kind of network or mining methods. And what we said is if you just think everything just a plain text, try to understand it very hard because it's not structured. But if we can structure that one into a network, it immediately becomes something quite interesting. Just give you a simple example like this picture. Okay. The center is a medical research paper. Okay, for example, it's about lung cancer, like how, they tried on different methods. What you can see is you have diseases in the paper. You may have proteins, you have genes, you have like different species, you have chemical compounds. All these things are in this research paper they linked, okay, because they linked by this research paper. Of course, you may want to understand much deeper, say what happened, whether this disease for this particular gene, can be cured in particular way, like particular drugs. Okay, it's important, but one paper, of course, you need people to digest and understand. But one important thing is, how could you find this paper you think is very valuable? You have to search. Okay, but people say things in many, many different ways. You may want to build a link, say this gene, and actually link to this disease in some non-trivial way. Non-trivial way means you find many, many papers, they actually show this linkage. Okay. If you want to get it, if we can extract these entities, like genes, disease, proteins, from one paper, you can construct a tiny network. But what about 30 million papers? You can construct a gigantic network. If this structured network can be mined, you don't have to read every paper. The machine will do it. Machine will do it in a much, much faster way, right? Because they can crunch millions of documents probably in a few minutes. There's no way you can do it. Okay. So what we are thinking about is the real network. A lot of real network actually contain multiple typed objects and links. They link together to form an information network, and this information network, if you all connect together, become very, very useful. Okay. Let's look at a few networks you probably will be convinced. Of course, you may say web is plain pages. Actually, web may not be. If you really think about a web, they may have certain structures. You can do mining. You also can do this game. Okay. But let's first look at medical network. Okay. If you think about, we actually work with Mayo Clinic, okay, including this new NIH center. Actually, part is UIC. Part is Mayo Clinic, one of the most famous hospital. Okay. So you have patients, doctors, disease, contacts, treatments, drugs, genes, all these things linked together. Okay. So that means if you just say, I want to find a patient network, of course you can find it. But just finding patient network doesn't make too much sense. You think about it. You got this problem, you want to be cured. Of course you can discuss with other patients, but you want to discuss with doctors. You want to find, what's a treatment, what's a possible treatment, whether the drug has any side effects. You want to know a lot of things, right? You want to know heterogeneous information, not just patient linked with patients, right? So that's the reason you need this heterogeneous network. Then we look at the bibliographic network. Like we use computer science publications. These are the research papers. Okay? But it's written by certain authors. It's published in certain venues. It contains certain keywords or topics. Actually, some people say, oh, I study co-author network. Okay? And they use co-author network, even try to predict new co-authors. Like why I want to work with him. Because I work with A works with B works with C, then I want to work with C. I actually asked one researcher, I said, in the real life, you work with C just because you work with A, and then A works with B works with C, then you work with C? I think it may not be true. Okay. In most cases, you find co-authors just because you work on similar topics. You want to submit to the same conference. You may cite even the same set of authors. That means you are really, really close. You study the same thing. That's why you want to work with him. Okay? So that's the reason we want to study heterogeneous networks, not just homogeneous, just author linked with author. You work with this author just because you work with other authors. What about you never publish any paper? You will never work with anybody? Okay. So that's the case. You will think a co-author relationship actually is mined probably from publications, authors, venues, papers, titles, topics, right? So that's why we said to study, of course, homogeneous network, you get all the single nodes like co-authors, friendships, or web pages that link together. It's fine. But in many cases, the homogeneous network actually can come from the original heterogeneous network. Just think about how they get co-authors. You get papers. The paper contains those authors. You get co-authors, right? It's the same paper ID linking with 3 authors. These 3 authors are co-authors. So you get a co-author network from the original heterogeneous network. That's why we study heterogeneous network. It's more real. It's more information rich. Okay. Now I just show you, for example, okay, you may have, these are the conferences, these are the authors, or you may have co-author networks. But if you get more than one entity, like one part is authors, one part is set of conference or venues, they link together, that becomes heterogeneous. But the homogeneous means the author only link with author, you lose all the other information. Okay? So actually, it's not very good if you do not consider it heterogeneous networks. Okay. Then we need to make another distinction. People say, I actually do not really study the pure homogeneous network. Somebody study, for example, WordNet. Anybody knows WordNet? Yeah, I saw quite a few hands. WordNet actually, I think, originally started from Princeton or someplace many years ago. And people study linguistics or English. They try to get similar words, they link together. Okay? For example, you say eat. The other guy may say, I have lunch or something. Then you may want to say, oh, this, you eat food and having lunch or something is close related. Okay? Then you have eat and meals can be linked. Eat and drink can be linked. Finally, you based on the semantic closeness, you get a big network. Okay. But this network, of course, from the semantic meaning, it is heterogeneous in the way is eat and meals are different things. Okay, one is an action, the other one is something to be eaten or something can serve as things to eat. But these things are not typed. You think about this, okay? If you link in a WordNet, you link all the similar meanings, like food, meals, eat, cookies and drinks, you all link them together into a very, very big network. Actually, it's not that easy to manipulate it, to inference things, because there are thousands or hundreds of thousands different types if you think in the types. Because you say banana is one type, maybe apple, But you have lunch, you have meals, you have eat, all things are linked together, but they are all different kind of types. It's not easy to do inference. If you get 20,000 entities linked together, suppose they have 10,000 types, it's very hard to do, to do mining and inferencing. Okay. What we like is small number of types, but they can link together. Okay. And that means we want typed heterogeneous networks. Let's see this one. Okay. Suppose you take DBRP, which is a digital bibliographic library, okay, of computer science. Okay. You get lots of papers. Paper is one type. Of course, it contains titles and keywords. The paper may contain a set of technical terms. So the paper linked with term is one type. Venue is another type, like conference and journals. Author is third type. You can see one paper, you may have 4 clear types. Okay. Once you type them together, for example, venue, you get all the different kinds of venues and journals, conference names. They mean something. Okay. And you get an author, you get a different author name, they mean something. They are strongly typed in the sense author is unambiguous, is author. Okay. Then you link them together into this typed network, they become very informative. Okay. You can derive a lot of things. Let's see, how we can get this typed heterogeneous information network to work. Okay. First, I give you some examples. You can look at this. Like the typical, research, you have bibliographic information networks. Like we have DBRP is computer science, archive actually contains, physics, chemistry, computer science, many, many papers. PubMed mainly is medical research publications. Then we have like a paper, venue, author, term. These are the types. The semantics is predefined. It's something like if it's author linked with paper, it means author writes papers. Okay. If venue linked with paper, it means this venue published the papers. And if the paper linked with term, means this paper contains those terms. So the semantics is very clear, very small number, but it's very succinct. Okay. Then you can play with it. You can derive lots of information. Let's look at even you play with tweets, okay, or some other social media like Facebook, Pinterest or LinkedIn or something. What you can see is like in tweets, you have a user, you have a tweet, you have hashtag, you have terms. Okay. Then you may have like follow. You may have post, you have retweet, you have reply, you have you may use certain terms, you may contain certain hashtags. So the semantic relation is also very clear. Okay. You look at a Flickr. Flickr, I do not know how many people know Flickr. Yeah, we got a maybe it's 1/3. Flickr actually, I remember many years ago, I think more than 10 years ago. Usama Fayyad, that time he was in Yahoo's CDO, Chief Data Officer. He gave me a cold call right in the summer. He said, I need to fly in. I need to give a talk at UIC, within 2 days. The reason is we want to set up a lab in Champaign, a new Yahoo lab in Champaign. I said, why you set up new Yahoo lab in Champaign? Why it's so urgent? He said, Motorola fire all those people. They close the center. Okay, there are lots of very talented technical people we want to get. Okay, and we cannot go late. If go late, other company will come and get them. We need to come right away, interview them. We can get a lab. Okay, he came the first time he came to UIC, give quite a big talk because it's quite a big name. Is one of the leads on KDD. Okay. The talk he talked is about Flickr because that time they just bought Flickr. Okay. They got this company. They just merged them. They probably spent $1 billion to get this company. Okay. And that's the first time I actually heard Flickr. They just say, for image processing, you want to label the pictures. It's very hard because automatic labeling, for example, you say this one is a building. What kind of building it is? Maybe it's an office building, or it's a university, it's a church, or it's just a shopping center. So you do not really know. Of course, you can ask image processing to do it, but image processing, very hard to even distinguish a shopping center with a stadium. Okay, you just think about it, you can take from many different angles. But human can do. Okay, so what they do is Flickr actually asks a human to label the image as a game. You get some small reward. The game is very simple. You just say, anywhere in the world, you can give labels. At the very beginning, this picture, nobody give you any label. Then you can just label. You say, this one is a building. The other one is also says building. Who is the judge? Once these two collide, you got like two people both vote for building. This one is a building, so the building token is used. Then other people have to give something a little more. For example, instead of a building, you say this one is Walmart. The other guy said it's Walmart. If this is really Walmart, the two people get a Walmart, then they collide. The Walmart becomes, then they can say different other things. They say this is a boring building, or this is a green building, or something. You can say something as long as people collide, they recognize this is a token. And if you get more token recognized, you get some reward. So it's a game kids like to play. But you automatically get millions of pictures labeled without writing any sophisticated, like image processing, image recognition procedures. And they know those procedures doesn't work well. Okay, so they got this one. That's the case. Actually, of course, the newly set Yahoo Center was not doing this. They just give you an example why Yahoo want to buy this one. Okay, this one actually has if you think the image is in a big network, you have users, tags, groups, and comments. Actually, this is the heterogeneous network again, because the user may upload the image. The image may contain some tags given by certain other users. The image may even have group tags belong to certain groups. The user may post comments. The comments may comment on this image or may associate with the image in certain ways. So that's the reason actually the image processing now was done by crowdsourcing. Okay, this is one of the very earlier one, but a very popular crowdsourcing, practice. Okay, and we also said the healthcare information network is very useful information network. I can give you thousands of such examples. People can see the information network is everywhere, and this typed heterogeneous information network is also everywhere. Okay. Now the problem becomes with this one, how we can do mining. Yes.
The links always have to be like action.
Actually, the question is whether the link must be actions. Actually, links carry certain type of information. Okay, you just think about this. For example, you can think this is a research paper. And the research paper contains certain keywords. Okay. You can say it's action, or you can say just a status. Or you can say this keyword is somehow linked with this document because the document is addressing these things. Okay. So essentially, the link represents certain relationships. The relationship could be verb, could be some status, but usually, for example, even you link with others, you say, that's my friend. That one is also, you can say, it's a status or it's an action. Okay. But to some extent, the link represents the relationship. The nodes representing entity. So that's a typical case. Of course, you can give me other cases. I think this is very general. But because you have different nodes, you have certain relationship, you use link to link them. Okay. Remember, you link two papers can be for many reasons. One could be citation. Like I cite this paper. This paper cite the other papers. I link it. Okay. Of course, you may have others say we contain same keywords. But usually, if we contain same topics and keywords, they don't, for homogeneous network, you want to link them together, so they are of the same topic. But for heterogeneous network, you actually link directly to those keywords. Like, for example, if you contain network, your paper contain network, my paper contain network, we all link to the network. Okay? So, of course, it means these two papers contain same kind of keywords. But the heterogeneous network is more explicit. To some extent, it's more useful because information-wise, it's richer, right? Now, I will give you a certain example. This is a very interesting, real example. Is this first author, Yi Zhou-Sen, she was a PhD student here. Now she's a professor in Northeastern University. I told you she actually working together with the same department, Barabasi, who is a big guru on network science. Okay. So this is just she actually used this one, just one entry of her paper. Okay. You can see this is her, the first author. Then you get several other authors. Charot actually is one in IBM research. Nitesh is a professor in Notre Dame. Okay. We four actually wrote a paper. She was taking the lead. That's her paper's title. When will it happen? Relationship prediction of in heterogeneous information networks. Actually, it's a very exciting paper. The paper actually gives you the result is she can even predict when you are going to cite the other paper, okay, or cite the other author. So that's actually, it's pretty hard. Even myself can hardly say when I'm going to cite it, like Christos Baloutzis. But she sort of can predict approximately how many months or how many years you're going to cite. Okay, so it's a little amazing result. Published in Wisdom Web Search and Data Mining this conference in 2012. You can see this is just a plain one publication entry. In DBRP, you have more than 2 million of such thing. Okay. Then what's the use of it? Of course, you can search, say what papers you wrote, how many papers you publish in which venue. Okay, that's a typical people use. But she was inventing a lot of new usages. Okay, that usage, she proved it can be done in a very, very reliable way and very interesting. Okay. She actually, her thesis, that's why her thesis in 2013 got the ACM KDD Dissertation Award. Remember, 1 year, there's only one internationally can get this award, and she got this award. You just look at those things, you will find that her thesis definitely is very rich. One thing is she can do ranking. For example, she can ask, who are the leading researchers on web search? This is a particular topic. She wants to find who are the leading researchers on this topic. You think it's not that easy, but she says, you give me 2 million entries, I link them as a network, I can find it. Okay. Another one is, who are the peer researchers of Yuri Leskovich? Yuri Leskovich, that time, just got into Stanford as a young assistant professor. But he was a star, okay, in the field. So she wants to know who are similar to him. Okay. Not in the age-wise or seniority-wise must be similar as well, because you just got a PhD. They want to find other people just got PhD also, okay, like young rising stars. Actually, to her own surprise, she found one is Qiaozhou Mei. You probably do not know him. He was Professor Zhai's student, got a PhD here, almost in the similar years. John University, Michigan, become a professor in Michigan, in Ann Arbor, and also very, very strong, published many, many papers, get very highly cited, get awards in KDD. And she found that Yuri actually is very similar to Qiaozhou Mei. Remember, the entry has 700,000 authors. You try to find a very similar one, like Yuri Leskovich. You can find she can find another young professor in Michigan, It's not that easy, right? You just think of a top 10 you can list. That's what I want you to do the homework, right? Find the top 10 similar ones. That's what she did. Okay. Actually, your homework is her one of the research papers. Try to use different measures, try to find the very similar ones. That's similarity search. Another one is a relationship prediction. For example, whom will Christos Faloulas collaborate with in the next several years? Okay. That's even Christos Faloulas may not know what who he wants to collaborate with, and she can predict something. Okay. And another one is a relation strength learning. That means which relationship most influential for author to decide her topics. And then you have a network evolution. How was the field of data mining emerged or evolving? That means as a data mining field in the history, where they started, how they evolved. Okay, you want to know the history. You want to do data mining, finding the whole history. And even you can find outliers, like which authors are rather different from his peers in information retrieval. We did find someone, actually, we published a paper with that professor's name, and he actually, for some reason, he almost, at the same time he read this article, he actually sent us email to protest it, said he's not outlier. Okay. But actually, the outlier doesn't mean it's bad. Actually, it means it's good, because he's not only published substantially in information retrieval, he also published substantially in bioinformatics. In the bio. That means he has double talents instead of one. Okay. And actually, if you even read Ito's recent paper, it's still very interesting. For example, she predicted for a particular bill which congressman and how they vote. Okay. Whether they vote yes or no or abstain. And predicted for this particular paper which one you want to citation. We actually have another student, Sharon, he published a paper on the citation prediction. Okay. That means you write a paper, what paper you should cite. Okay. So those are the very interesting things, and you can do in a very high quality. It simply says, the heterogeneous information network contains lots of very rich information. Okay. And what are the methodologies she developed? She not only solved these problems, but she developed several very interesting methodologies. One is information propagation across heterogeneous nodes and links. Simply says, when you link to the other things, the general philosophy is you must have some relationship. That means, for example, if you publish this paper in the KDD conference, likely you are doing KDD research. Otherwise, why are you publishing this conference? Okay. That means I actually may know you link to this conference means you are certain kinds of authors. Of course, it's not 100% certain, but you have certain probability linking to certain fields based on the keywords, based on the conferences, based on the authors, based on the papers. The information can propagate. Okay. One paper may not tell you much, but if you get 50 papers, I'm pretty sure what kind of research you are doing, right? So this is information propagation by links. Okay. Then the second interesting thing is search and mining may have network metastructures. What is network metastructures? If you think about the previous link I give you, you probably can see you got a paper linking with venue, linking with keywords, linking with authors. Those are the metastructures. Okay. And this metastructure, some can be stretched pretty long. For example, you want to find co-authors, or you want to find people usually publishing the same venues. You can stretch very long because you got a paper, okay, the other people get a different paper, but then they link to the same venue. Okay, so those are the things you can see this meta structure quite useful. Another lesson or method she has developed is user-guided exploration. That means if you do not know what meta structure is useful, okay, you can give a few examples. Once you give an example, the computer, the system, the algorithm is going to figure out what is the most important meta structure your semantics may imply. Okay. Then we can use user simple guidance to find the hidden relationship of those meta structures. So that's what she actually worked out. Okay. Now I'm going to give you a little more detailed papers and examples which contain lots of technical stuff. Anybody knows where this one is? Okay. This actually is City Hall of Stockholm. This is the place every year the Nobel Prize for science, physics, chemistry, medical science, including literature. Only the Peace Prize is in another, I think it's in Oslo. Okay. All the other Nobel Prize actually winner will get into here to get an award. Okay. So this is a very well-known structure, okay. Very, very huge as well. Now we get into the first interesting study by her. Actually, it's a very, very good one. Is clustering and ranking. Okay. And the first important thing is everybody knows ranking is very important. That's where PageRank comes, right? You get a paper or you get an author, you want to find him just by keywords, and that author's most important information must be ranked very high. Otherwise, if it's hidden in the 50,000 entries, the web is not used for anymore. Right? That's why Google can give you the PageRank. The rank is very important. Clustering is also very important because you think about it, you get information about a disease, suppose a lung cancer. You want to find related information already in the same cluster, so you can tour around, you can find the most important information. Right? But very few people want thinking about this clustering and ranking as a function. They should work together. They should be found at the same time. Okay. She was the first one actually thought about this. The interesting thing, the first question you may ask is, how do you get a rank? Okay. Of course, that time PageRank already come. You can say, oh, I just use PageRank. Okay. What about there's no links? Okay. There are links. In many cases, semantic-wise, you can link as heterogeneous networks. You do have heterogeneous networks. But how these heterogeneous networks can give you clusters and ranks. Okay. The first important thing is, if you study cluster, actually I have a Coursera course on cluster analysis. It runs for 4 weeks if you want to know the clustering methods. But majority of clustering algorithms treat every point, every object identical. Okay, the same thing as like a classification. Classification, you say this example, you make it wrong. I give you certain points off. I'll give you the accuracy lower down. They treat everybody just the same. Okay, if I give you 10 things, you have 7 things got right, 3 things got wrong. I said your accuracy is 70%. Okay, so everybody thinking every example is the same. But she was thinking why everything must be the same, must be the same weight. Just thinking about it, if you cluster like the last year, Mike Stonebreaker, who was a database researcher in UC Berkeley, now in MIT, he got a Turing Award. Okay, we're quite often using him as an example. He's a die-hard database guy. That means he doesn't work on anything. Like he doesn't work on AI, doesn't work on like distributed systems or cloud. He doesn't work on anything except just work on database. Okay. And his ranking is very high. That's why he got a Turing Award. Okay. So if you do cluster, okay, just thinking, suppose you are doing database. You say, I'm the first year master student doing database. I actually have a technical report. I just want to send it to a conference. Okay. Suppose my clustering algorithm cluster you and Mike Stonebreaker in the same cluster. Okay. Which one is important? Of course, Mike is important. If I make it wrong, my clustering algorithm put you inside, but throw Mike Stonebreaker out, everybody will say this is ridiculous Because if Mike Stonebreaker is going to do AI, the whole world, whole computer science will become a breaking news, right? All the people say, oh, I probably have to change as well. So that's a very big shocking news. But if you say, I'm not doing database anymore, I'm doing AI, who cares? Right? So probably only your advisor may feel a little sorry. That's it. Okay? That simply says, if I put you in the wrong cluster, probably the cluster structure is as good as before, right? But if I put a Mike Stonebreaker there, wrong, no, it would be ridiculous. That simply says, no matter you do classification and clustering, the rank actually play an important role on the quality. We should not just judge everything, just one sample is one sample, right? But the problem is, how could you find Mike Stonebreaker rank higher than you? Okay. Of course, you may say, oh, because he published more papers than me, right? So that's a count. But actually, if you think about the information network, all things are linked. You use this network to do clustering. You may be able to get a ranking and clustering finish at the same time in a nice quality. Okay, so that's the reason she first worked out an algorithm called rank class. Okay, and later she actually worked out even more on the more sophisticated network called net class. It happens, you see, this is a 2009 paper. I think our student in my group actually checked. Every of these two papers got over 200 citations now already. It simply says that people really, really like the paper. Many researchers follow her work, actually it's cited. Let's first see how she worked out this algorithm called rank class algorithm. Okay. The first interesting thing is she got this network. She first studied the simplest ones, only 2 types. Remember, we said the network may have 4 or 5 types. Like you have author, you have paper, you have venue, you have terms, you get more types. Suppose the simplest one is only two types. Okay. We get 2 types. One is venue, like conferences or journals. Another one is author. Okay. If you got a paper published in Sigmod, I give a link to you. Okay. If you publish another paper in VRDB, I got a link to you. Okay. Then I can form this network just as bi-typed, in the sense I can have one side is one type, the other side is the other type, they link together. But this is different from bipartition network. Why? Because you look at those red links. Red links means if they are co-authors, I can link them together. Okay. The co-author means that they are in the same paper. But because this one has no paper information, actually you will have no way to know they publish in the same conference, whether they co-author paper or they are just different authors, different papers in the same conference, right? So that's why you do need this link to show they are, the authors are linked together because they are co-authors. Okay. Then, if you write in the matrix form, remember we said that the network or matrix, you can write as an adjacency matrix if you link together. But now you have different links. For example, if we say X, this left-hand side, this X is venue. Okay. The right-hand side, Y, is author. Then you may have the links, you may have the network, the adjacency matrix, in 4 different parts. One is XX, means how the venues are linked. Okay. Initially, the venue are not linked. There's no explicit link linking Sigmod and VRDB. That's why XX initially is empty. Okay. There's nothing there. Everything is 0. But X and Y means this is venue linking with author. You will have the real value. Like you publish papers, I link that. If you publish 2 papers, I may have the weight as 2 linking to this venue. Okay. Then YX, this is a symmetric. X linked to Y, Y linked to X. This is venue and author linked. This YY initially just co-authors. These 2 authors publish the same paper. You have 2 co-authors. Initially, it's not empty. Otherwise, it's empty. Okay. That's the initial one. Then with this, you will be able to kick in the like a clustering algorithm. You may find clusters. Okay. But the clustering algorithm, if we consider this clustering algorithm not simple clustering algorithm, we need to take care of the ranking as well. In your design, you need to think about how to do ranking. Okay. Ranking must have a score. Say, for example, like you just said, if Mike Stonebreaker published 200 papers, of course it's more than that, then this link, I put a weight as 200. If you publish one paper, I put a weight 1 to your linking to that conference. That's a very simple ranking. You get more papers, you rank high. Okay. So if you got a very simple ranking, how do you work out this ranking formula? Okay. You can see X is a venue. Y is author. The venue's rank, how do you work it out? You can work out the formula like this. You can see you got, suppose this one is X is one venue. Okay. Then this J is author published in this venue. You can see this J is one author. Then you get all the authors, J from 1 to N. You get all the authors published in this venue. Okay. Then you actually were, if your venue take more authors, more papers, you will be ranked high. Okay, that's the idea. But you have to divide by, you have to normalize it. Normalize it means you actually were thinking about this I is not a one venue. You have to think about all the other venues, right? You finally add them together and say which portion you were, because if every venue take 1,000 papers, we are equal. But what about your venue only take 10 papers? It's a small workshop. A venue take 100 papers. So maybe I have a higher ranking than you, relatively. So that's the reason you need to normalize it. You take all the venues and all the authors, you just add them up. You get the denominator means all the venues, all the authors, you publish papers, you all add them up, right? So you normalize it. That means if your conference in the whole field, taking a lot of space, likely you could be ranked high. Okay. So this one is for authors. That's the same idea. You can see for authors, how do you rank authors? If you publish in more conferences, more times, you'll rank high. Okay. Then you have to normalize it according to all the authors, all the venues. Okay. But you may say, is this a very good ranking rule? It may or may not. You think about this. Suppose you follow one professor. The professor may not be very good, and all his paper, including yours, got rejected by the conference. And the professor said, don't worry, we set up our own conference. Every paper will be taken. Okay. So you got publications. Are you very happy? Okay. Of course you say, oh, I do have a publication. But other people say, this could be a bogus conference. You probably remember, I do not know whether you remember it. I think of many years ago, there was, MIT has a natural language group or some kind of a computer science group. Those bogus conferences keep asking those MIT PhD students, say, send papers to me, your paper will be get accepted. Okay. And those students got bored. They found a way. They use random number generator, generate a fake paper. The paper actually is grammatically and the outlook really look like a nice paper. You have formulas, you have papers, you have lemma theorem, like abstract and references and pictures, everything, curves. Okay. And he generated 2 or 3 papers, sent to this conference. And every paper got accepted. Okay. Actually, of course, if you really read the paper, it doesn't make any sense. But every sentence is correct. Okay. It's correct English-wise. So it became a big news. Actually, even New York Times interviewed the conference organizer. Say, how could you accept this paper? It doesn't make any sense. Okay, because the paper will be reviewed by 3 reviewers. How could that paper be accepted even does not make any sense to anybody, right? It's just generated by machine. Okay. Of course, it's a big embarrassment. I think the conference later just collapsed or closed because it does not have any reputation. Okay. It's just a joke. So that simply says you may not want to consider a venue which actually is just count numbers. Okay. Then Izhou actually work out to say that simple ranking, just counting the number, may not be the right one. Let's work out a better one. That means I do take care of the reputation. But the problem becomes, who will give you the reputation? Is it, is some god or, some people, authority in computer science say this is ranked number 1, the other one number 50. Nobody give you this ranking because people will start fighting. Right? So the interesting thing is you can easily work out a formula which can take care of this ranking. Just think about this. Okay. What you need just to set up a few rules. Then when you do the counting, you follow these rules. Okay. She actually easily set up 3 rules. It happens these 3 rules work out quite nicely. The first rule said highly ranked authors publish many papers in highly ranked venues. Okay. That probably you would agree because if this venue rank high, you got a paper in. Like this Friday is a KDD deadline. KDD is a top conference in data mining. So many of my students actually working really crazy. I actually got a few draft at 4 a.m. this morning, right? Simply said they really work overnight. They get at 3 or 4 a.m. and still working on it. They just wanted me to have a look. Okay. So that simply says why you want to get your PhD, you want to publish in the highly regarded conferences, just because if this conference rank high, you publish more papers in this highly ranked conference, people will view you highly because the competition is high. Okay. You can get a champion in Olympics, then people will respect you. But if you just get a champion within, within your group in kindergarten or something, nobody will care you, right? So that's the reason you can see this is ranking of the venue. This is ranking of you, of the author. So you publish more highly ranked papers, you get a better ranking. That's a very simple rule, right? Now you do not do the simple normalization, you can see, okay? Then rule 2 is, actually this one is a little twisted. I probably should adjust it a little because otherwise something may not be able, I think it's just, for Microsoft, sometimes the spacing will change for different machines. Okay, at least now it's a little better, okay? So, okay, it's still not very good, but you can read it. The rule 2 is highly ranked venues will take many papers from many highly ranked authors. Okay. Remember, actually, that's why exactly I want to show it, because there are 2 Italian-sized many. Okay. That means not only you publish many papers, you take many papers, but you take many papers from many highly ranked authors. That, if you look at the formula, this is author's ranking. Okay. The author's ranking, if you take more from those highly ranked authors, your venue will be ranked high. Okay. That immediately rule out those bogus conferences. Like suppose your bogus advisor, okay, set up a bogus conference taking every paper from you. Okay. You think a very, very common sense is any highly ranked author will join this conference? Probably they will never. If you think about it, if you publish random number generated papers, then those authors will not want to send to your conference because you already got a reputation in publishing random number papers. Why people want to get the same insult, right? So to that extent, this is a pretty simple rule. You can rule it out. The third rule is very interesting. Is the rank of an author is enhanced if he or she co-authors with many highly ranked authors. Okay, that one actually is in common sense. You probably know the reason is this. Okay, you think about it, especially for young researchers. If you want to get a rank, you may only publish 1 or 2 papers or a very small number of papers. But if you publish in a very, very good venue, co-author with very big names, okay, so simply says your rank will be higher. Okay, you think about this. Okay, suppose Mike Stonebreaker is Turing Award winner. If you co-author a paper with Mike Stonebreaker in database systems, likely you're pretty good. Okay, otherwise he won't take you, right? It's more like you co-author a paper with Einstein in physics. You must be something, right? Otherwise, why Einstein will co-author with you? It's the same idea, right? So this one, if you see, actually this YY means co-author. Okay, remember these are 2 Y's. Okay, actually this alpha is parameter can tune. That means you can, based on your community's culture, okay, you can tune this. You probably know in physics or even in biology, sometimes you get thousands of people co-author 1 paper. Remember the Higgs? That one got a Turing Nobel Prize because it found this is called God particle. Okay, this Higgs. Higgs probably has several thousand authors. I do not know how many thousands, but they said just the names printed quite a number of pages. Okay, just that paper, published in Nature or in some very, very famous place. But because there are thousands of people join this effort, they even put all the people. I do not know whether they put cleaning work, but at least you are fixing the machine. They put your name down there as well. So that's the reason they got a very big number of names. Okay, so if that's the case, probably they want to make this weight a little smaller. Okay, because otherwise even you got Nobel Prize, not everybody can get Nobel Prize, right? So it's only 1 or 2 people will get it. So that's the reason you can actually work this out using those rules. Okay, then you look at the methodology. The methodology actually says every object in the cluster may have different ranking. Okay, you have to calculate not only the cluster but also the ranking. But now when you want to do the clustering, every object will weight differently. That means if this one is highly ranked, highly weighted, then in your clustering, this one will take more weight. Okay, and the ranking only will make sense within this cluster. Like Einstein only ranked high in physics. Like Mike Stonebreaker ranked high only in database. Right? You go to AI, he may not rank high. Okay, so that's the reason you actually find a different cluster. You have different weights. It's a distribution of the ranking. For example, in computer science, suppose there are 10 different fields. Okay, Mike Stonebreaker may have a very high weight on database, but maybe very low weight on AI or distributed system or theory. Okay, so you have a vector. The vector has different weights. Then the different weights put you into the different cluster with different weighted factor as well. So then you can do good clustering. Okay, so that's the general philosophy. Of course, you can work out many more ranking rules. For example, in some society, they may weight journal higher than conference or vice versa. Right? And there are many other ranking rules I'm not going to discuss, but you can refine this algorithm in many ways. Okay? But the thing is, she actually put this weighting and the clustering, into a major algorithm called EM algorithm. I do not know how many people knows EM algorithm. Yeah, we got to probably be 1/3. Okay, I'll give you a little introduction if you do not know. But I probably have to ask you another question. How many people know K-means? I would definitely have much more people know k-means. K-means is a very basic clustering algorithm. If you do not know k-means, simply say you do not know clustering. Okay. The k-means, the general philosophy is this. At the very beginning, you have many points. You're just thinking about the spatial data. You have many, many points in the different locations. Okay. You want to find the clusters. Okay. The k-means, at the very beginning, you can randomly, suppose you want to find five clusters, you can randomly assign those points to 5 clusters. At the very beginning, you can do some very poor job. But the k-means basically saying at every iteration, you will re-evaluate the cluster center. Okay. Re-evaluate cluster center means you may get a very ugly cluster, but you can get a center for this ugly cluster. Okay. Then once you get the center, you will say something closer to me, where I will recruit you to my center. Something far away from me, but if you are closer to the other center, you belong to the other center. Okay. So then they will reshuffle it. Once they reshuffle it, next iteration, they are going to re-evaluate the center. Then they reshuffle the points. After certain iteration, all those clusters are reasonably nice. Reasonably nice means in the same cluster, they are closer. Okay. In different clusters, they are far apart. Okay. That's general philosophy. Okay. And for EM algorithm, it is essentially as a soft k-means. Soft k-means means the k-means said you are either in cluster A or in cluster B. There's nothing in the middle. Okay. But for EM algorithm, every point is a probability distribution. Or you can say it's soft in the sense, if you say, for example, suppose computer science has 10 fields. You publish some papers. You can say, I'm, say, 50% in data mining, maybe 20% in database, and maybe 10% in AI, maybe 3% in theory. You can have a distribution. Okay? That means I can recruit you only in the proportional way. I can re-evaluate you in the soft way. Okay. So it's a soft clustering. So the soft clustering has 2 major steps. That's why they call it EM. E means expectation. M means maximization. Okay. The expectation means if I can work out a center, okay. If, for example, this center is a database center, that center is the theory center. Okay. If you publish more papers or work more on the database field, so I expect that you belong to me. Okay. At least expect more. So this expectation means somehow I assign you softly to certain centers based on a probability distribution. Okay. That means I can assign you to a database just because you publish more paper in database. Okay. So this one is similar to k-means. K-means is to hard assignment. The expectation do a soft assignment to the closest center. Okay. What is maximization? Maximization means I recalculate center based on all these objects. That means if the database now shifted more towards AI, probably my center will shift more down there as well. Okay. So I just recalculate the center. Okay. Then I go back to the expectation again, I reassignment, then I recalculate. But the difference is everything is soft. It's based on the probability formula. Okay. So essentially it's a statistics. Okay. The EM algorithm is basically saying you take the E step, you assign object to the cluster based on the probability distribution, based on some parameters. Okay. Then the M step is try to find a new parameters or clustering or new centers, okay, to minimize the sum of the square error. Okay. So that's the general philosophy. Now, she was using this to do the whole computation on the networks. Okay. And how do you do the computation on the networks? We just look at the bi-typed network. Okay. The bi-type network means you look at every object. Suppose you say, I want to get 5 centers. You look at every object at the very beginning. Of course, you still can assign based on, I can randomly pick up this one in the center. You can assign them based on the evaluation. Based on it's closer to this, you sign this. Okay. The closer to this from the network point of view could be if I sign this one as a database, you're close to the database just because you're linking those things closer to the database. Okay. So everything at the very beginning is just a probability distribution. That means you have a center cluster K. Then this object, which is, this one is a venue. Remember, X is venue, Y is author. The venue, you have a probability distribution to this cluster center, and the author also have probability distribution to the center. You can sign this. Okay. Then you, based on this, you can do ranking just because you can use a ranking rule. Like the simple ranking means you publish more papers in this one, you sign better, higher weight. Okay. And the authority ranking means you publish more in the highly ranked conference, you sign more weight in this one. Okay, so this is you use this EM, you keep doing this. After certain iterations, things will become stable. You get a very good ranking and clustering. Okay, so the whole framework is this. At the very beginning, you can randomly partition them into different clusters. Like you give me a K, I partition you into K clusters. Then I, based on the ranking rule, I can assign venues and a conference to a certain cluster. Okay. Then I can evaluate them. I can create for every object, I can create a mixture of coefficients. Essentially, it's a weights. Okay. Then once I get a weight, I can adjust the clustering. Then I go back, redo the ranking, because the center is changed, redo the ranking, redo the clustering, until the change becomes very minimal. Then I can stop. So this is the algorithm called rank class algorithm. Okay. And in the next lecture, I'm going to extend it. Instead of just saying two objects, we're going to get a star schema, get a much bigger one. Okay. Then we'll see how this philosophy may work. Okay. Yeah, thank you.